Hi guys, in this video we're going to talk about transformations of both exponential and logarithmic functions. So first let's start out with this equation here. This is what it looks like with all of the transformations applied. Okay, so for the a value, and you notice that this is an exponential function because we've got this up in the exponent, and we don't see the word log anywhere, so this is your transformations for exponential functions. So the a here, just like a in the other things that we've ever talked about with transformations, the a causes it to vertically stretch or compress. Okay, it could also cause it to reflect. Okay, if it reflects, it would be reflecting over the x-axis. And that's, of course, if the a value is negative, less than 0. Okay, the h here, remember, if it's inside with the x, okay, this is up in the exponent with the x value, okay, that's going to shift it left or right. And then the k value, this is not up in the exponent, it is like in addition to the original function. That's going to shift up or down. I like to say that the k is on the outside and the h is on the inside. If it's paired up with the x, it's what I consider to be on the inside. And don't forget, if it's on the inside, all that horizontal movement, it's the inverse of what you're actually seeing. So if it says -3, it's actually to the right 3, okay? There could also be a reflection across the y-axis. So if we wanted to reflect it horizontally, which would be a flip like this rather than a flip like this, okay? So horizontal flipping reflections, that would be up here if this value is negative. So you could have horizontal stretches and compressions here, but we're not really going to focus on those kinds there. Maybe you might have a reflection here, so if there's a negative in front, we want to say it reflected over the y-axis. And that's, of course, if the value in front here is negative. All right, so what we're going to do is we're going to talk about some really important stuff and try to identify transformations that have taken place. One key thing to remember, one of the most important things, you don't have to have a calculator to do this, but if you recall, exponential growth function looks like this. Exponential decay looks like this. And in each of these cases, right here along the bottom of both of them, that's where the asymptote is. And since exponential functions have a horizontal asymptote, any movement vertically, so any movement up or down, you're shifting up or down, is going to cause that asymptote to move. So let's just start with this first one. It says first identify the transformations. Well, we've got a times b to the x plus 2 plus 2 here. Okay, so the transformations that we see, go one at a time. This first one here is a vertical stretch. So it's been vertically stretched. I'm going to say vertical stretch by 5. Okay, now the 2 here, that is my base value. So my parent function would have been 2 to the x power. That would have been the parent function. Okay, anything in addition to that is all the transformations. So I see plus 2 here. Well, plus 2, remember, we're thinking inverse because it's with the x. So that has been shifted to the left 2. Okay? And then we have a plus 2 here on the outside, which means it went up 2. Now, by doing all of that, if the original looked like this, and this was my x-axis, and this is my y-axis, and if I shifted it up 2, let me get a different color here. If I shifted it up 2, it now would look something like this. So the original asymptote that's here at 0 is now up 2. Okay, so this orange one represents my transformed graph. The asymptote is now at y equals 2 because it went up 2. Okay, the domain, well, the domain did not change because this graph still will go forever and ever as wide as it can. So the domain is still all real numbers. The range, it has changed because the asymptote moved. So originally we weren't going past 0. Now we're not going past 2. So from 2 all the way up is where we are. So y such that y is greater than 2, that's my new domain. All right, let's try the next one. So we have a vertical stretch by 3. The base is the 1/2, so that has nothing to do with any movement because 1/2 has the exponent, okay? So the parent graph would have been 1/2 to the x power, okay? So we shifted, since it says -1, you think inverse, we shifted to the right 1, and we also shifted up 1. All right, so if we have our graph, original, the parent function would have come in, it's a decay because this is less than 1, so it would have been shaped like this. And now we've moved it up 1. And up here on this one, I did not shift it to the left 2 like I should have. It should have been over here somewhere, of course, with the stretch. But my main goal there was telling you that the difference where the asymptote was, okay? So I'm not going to ask you at this point to graph the transformations, but I want you to be thinking about where the asymptote moves, okay? In this case, remember, you have a horizontal asymptote. Any movement up or down moves the asymptote. Since we moved up 1, the asymptote goes up 1. So now the asymptote will be right in here. Of course, with all of the shifting, your graph would look a little bit different than this, but I want you focused on the asymptote. So since it moved up from the y equals 0, from the x-axis, it moved up 1, so now the asymptote is at y equals 1. Of course, if it moved down 1, it would be y equals -1. All right, the domain didn't change because we can still stretch it forever and ever left and right, so all real numbers there. And the range has changed now because the asymptote moved. So we're not going below that asymptote. So it's y such that y is greater than 1. Of course, if there was any reflection, you'd have to take that into account when you're looking at your range. All right, now let's try to write one. Okay. You're given a parent function, and you're going to apply the transformations that I've asked you to do here and write the new function. Now the key is we need to give this new function a new name. Right now it's called f of x. So I'm going to call the new function g of x. You could call it h of x, you could call it p of x, it doesn't matter. This just tells you that it's something different from the original. Alright, so we know that our base is 3 and we're raising it to the x power. Now we have to apply our other information. It says it wants you to reflect over the x-axis. Well, any reflections that are happening vertically are applied with the a value, okay? So any stretches or compressions. We have a vertical stretch here by 3. So I'm going to multiply this by a 3 for my vertical stretch, and I'm also, for reflecting, I'm going to make it negative. Okay? Then I'm going to shift to the left 2. Well, horizontal movement is up with the x, and it's the inverse. So this is saying shift it to the left. I would think in my head negative, but I'm going to write positive 2, plus 2 there. So when I look at this now, I'm going to say, oh, that moved left 2, okay? And then shift down 3. So on the outside, minus 3. And there you have it. That is your new transformed function. All right, I'm going to stop here. I'm going to make another video for the logarithmic functions, and then you'll be responsible for your homework on the back of these notes, and we'll go from there. Ask me any questions if you have them.